Okay, this video is in the acids and bases topic, and it deals primarily with Arrhenius and Bronsted-Lowry theory of acids and bases, and these are the two main theories that you need to know about acids and bases for Year 11 ATAR chemistry. So, before we get on to Arrhenius and Bronsted-Lowry theory, what we're actually going to do is we're going to recap on properties of acids and bases. So, as you can see, these are the properties of acids and bases. Acids taste sour, whereas bases taste bitter. Acids are corrosive. Bases are also corrosive, but bases tend to feel slippery. The reasons for this are partly due to the corrosive nature of them, and also similarly they convert oils and fats in your skin to a soap. Both acids and bases will typically conduct electricity, and we'll see why that is in a little while. Acid reactions that you should already be familiar with, they react with carbonates and also hydrogen carbonates, which you won't be so familiar with, and they form carbon dioxide and water plus a salt. They also react with metals, reactive metals, so not copper, not silver, not gold. There are others, but they're the three main ones. And they produce hydrogen and salt, and acids and bases will react with each other and they form water and a salt. And this is typically referred to as a neutralization reaction. If you have the appropriate quantities of each, then essentially you end up with water and a salt. And water, as we know, is not corrosive and doesn't carry out any of the more aggressive reactions that either acids or bases will. Okay, because most acids and bases are colourless and they have some properties which are very similar, we can use indicators to determine not only whether they are an acid or a base, but also what pH they possess. So litmus is red in acidic conditions and blue in basic conditions, and also another indicator, phenolphthalein, that's colourless in neutral and acidic conditions, and it's the violet pinky colour you can see in basic conditions. We'll discuss pH in a later lesson, but for now you should be familiar with the idea that something with a pH of 7 is commonly referred to as neutral. That is only the case at 25 degrees C and at 101.3 kilopascals. If the temperature is higher or lower, then neutral can actually be a pH other than 7. So we'll discuss that probably in greater detail, possibly in when we look at pH, but it's also discussed in year 12, and you find out the reasons why the pH can vary then when we deal with equilibrium. So, on to theories of acids and bases. So the first theory is Arrhenius theory, and that you need to know about. And there were theories that were precursors to Arrhenius theory, but this is really the basic entry point into what is modern chemistry. So Arrhenius defined acids and bases thus. So an acid has hydrogen in its formula, and it dissolves in water to form hydrogen ions, H+. A base has OH in its formula and dissolves in water to form hydroxide ions, OH-. So you may say, well, from what I currently know, that actually seems to sum up acids and bases quite nicely, and indeed it is useful for classifying acids and bases, but other substances do have acidic or basic character, and they don't necessarily fit this definition. So what we're going to look at in the next slide is what the problems are with Arrhenius theory. Now, some of them I will be able to demonstrate in a lesson, and others we will kind of discuss in a little bit more detail, and you'll find out about them in some practical work that we're going to do. So, what are the problems? Well, one of the problems is that there are substances that produce hydroxide ions in solution, but they don't actually contain OH in their formula. So two examples are ammonia, which some of you will be familiar with is a base, and the carbonate ion. So if you dissolve something like sodium carbonate into water, you actually end up with a basic solution. And it is one of the main problems with Arrhenius theory. Arrhenius theory only applies to a substance in water, but there are acids and bases that exist in other solvents as well. So Arrhenius theory is really only applicable to substances in water, but because acids and bases exist in other solvents, there's a problem with the definition that he came up with. There is a reaction between hydrochloric acid and ammonia gas, and this can't readily be explained using Arrhenius theory. So it actually forms ammonium chloride, and I'll show you in a demonstration that reaction later. There are many salts that are produced which actually behave as either acids or bases, and you'll learn more about that in year 12. One of the other biggest problems with Arrhenius theory is the H+ ion does not exist for any really measurable time in water, all right? And what happens is it will react with water and it will form H3O+ ions. Now, H3O+ ions are called hydronium ions, and it's one of the main kind of foundations of the other theory that we're going to learn about. So, what is the other theory? Well, the other theory is Bronsted-Lowry theory. Bronsted-Lowry theory basically says that acids and bases cannot exist in isolation. So while Arrhenius theory says, okay, well, a substance dissolves, it produces H plus ions, therefore it's an acid. A base dissolves in water and it produces hydroxide ions, and therefore it's a base. What Bronsted-Lowry theory says is that you cannot have one thing without the other being present. And this is summed up by the two boxes in blue. And Bronsted-Lowry theory says the reactant that loses H plus is called the acid, and the reactant that gains the H plus is the base. That means that when you have an acid, there must also be a base. So an acid-base reaction is one that involves the transfer of a hydrogen ion, H plus, from one reactant to another. So that might kind of be a little bit difficult to understand, and it's probably better to actually illustrate it with a reaction. So let's have a look at an acid-base reaction according to Bronsted-Lowry theory, and we'll see how we go about actually identifying what's an acid and what's a base. So I use this three-letter acronym to just assist with remembering what we're talking about. So a base is a proton acceptor and a proton donor is an acid. So PDA, BPA. Okay, and I'm sure you can come up with some rude acronym that will help you remember those three letters for each, right? So proton donor is an acid, PDA, base is a proton acceptor, BPA. So let's have a look at a reaction. Okay, so in this reaction we've got water. You can see water here, and we've got this substance, which is hydrogen sulfide gas. Now, if you look between the hydrogen sulfide gas and what it's actually ended up as, my pen's not working very well. The H2S has lost one hydrogen. So from here to here, we should be able to see, okay, well, it's lost one hydrogen. That means that this has donated, the hydrogen sulfide has donated a hydrogen ion. So this is a proton donor, all right? So it is acting as the acid, going from this side to this side. Okay. Now the water, on the other hand, if you look at the water has accepted a hydrogen ion, a proton, and so the water in this case is acting as the base. So remember I said to you that Bronsted-Lowry theory says that acids and bases cannot exist in isolation. They always exist in an acid-base pair. So on this side, you can see that the base is accepting a proton. So H2O, it's gone up one hydrogen, therefore it's the base. The acid is the hydrogen sulfide gas because it has lost an electron. It's donated the proton to something else. Okay, now you can see that there's a double arrow in the middle. And for the reverse reaction, so going from here to here, the H3O plus is acting as the acid because it's losing a proton, and similarly going in this direction, the hydrogen sulfide ion is gaining a proton, so this is acting as a base. So you can see that for the hydrogen sulfide ion and the hydrogen sulfide gas, these two are related to each other. And what we say is that these are a conjugate acid-base pair. Okay, so these are the same substance. On one side it's acting as an acid. The conjugate base of that acid is the hydrogen sulfide ion. Similarly, the water on this side is acting as a base. Its conjugate acid is the H3O plus ion, the hydronium ion. Okay, so we've dealt with these 2 points. And what about the reverse reaction? Well, in one direction it acts as an acid. The conjugate base of that, if we go back the other way, is acting as a base. Okay, so that's essentially Bronsted-Lowry theory. What it says is we always have an acid and a base, and the thing that goes up one hydrogen, that's acting as a base because it's accepting that hydrogen ion, it's accepting that proton. The thing that is losing a proton, that's the thing that's the acid. Okay, and it's that simple. So really, when you're trying to identify what's an acid and what's a base, according to Bronsted-Lowry theory, you're just looking at how the hydrogens change from one side of the reaction to the other, and it's that simple. Okay, so there are substances which are amphoteric, amphiprotic, you can call them a number of different things, but water, you can see in this reaction, is acting as an acid. Okay, so from here to the related item over here, the related species, it's dropped one hydrogen. So it's donated a hydrogen. The ammonia here, that's acting as a base because it's gone up one hydrogen. So now it's NH4+. So this is ammonia, this is the ammonium ion. And this kind of explains why ammonia, when you dissolve it in water, is basic. Because it produces hydroxide ions, but it doesn't actually have any in it. So that's one of the problems that we had with Arrhenius theory, if you remember. Similarly, water can also act as a base. So if you look from here to here, you can see that this has gone up one hydrogen, and so this is acting as a base because it's accepting a proton. Okay, bases are proton acceptors. And similarly, the hydrogen chloride gas is acting as an acid because it's lost one hydrogen. So you can see that water is a very interesting substance because it can behave both as an acid and as a base. And as I say, these are sometimes called amphoteric, they're also called amphiprotic, but really it's just a substance that can act as both an acid and a base. Okay? So, I've talked a little bit about this already, conjugate acid-base pairs, but just to drive the message home, you can see that in the reaction, the sulfuric acid in red on the reactant side of the equation has one more proton than the hydrogen sulfate ion, which is on the right hand side of the equation. So that means that the sulfuric acid, unsurprisingly, is acting as an acid going from left to right in the reaction. The hydrogen sulfate ion, therefore, is the conjugate base of sulfuric acid, H2SO4. Okay, so HSO4 minus is the conjugate base of H2SO4. Similarly, if you look going from water to the hydronium ion, H3O+, you can see that that has gained one hydrogen, and so the water in this instance is acting as a base going from left to right in the equation. That must mean that H3O plus is the conjugate base of H2O. So when we talk about conjugate acid-base pairs, the species basically either goes up by one hydrogen or down by one hydrogen, and that's what you are looking for when you're asked to identify conjugate acid-base pairs. So don't fall into the trap of thinking sulfuric acid is the acid, water is acting as the base, therefore water is the conjugate base of sulfuric acid, because they're not related to each other. Water is distinctly different from H2SO4. Okay, so conjugate acid-base pairs, they must just vary by one hydrogen. Okay, so that's what conjugate acid-base pairs are. Okay, so when it says and vice versa, we can say that going from right to left in that reaction, the hydrogen sulfate ion, HSO4 minus, to H2SO4. HSO4 minus is acting as a base going from right to left because it's accepting a proton to form H2SO4. So the hydrogens have gone up by one. So going from right to left, the hydrogen sulfate ion is a base and H2SO4 is its conjugate acid. And the same applies for the hydronium ion, H3O+, although H3O+ is acting as the acid because it's losing one hydrogen to form H2O. So H3O+ is the acid and H2O is its conjugate base. So because the reaction shown by the double arrows, it can go in both directions, either stating it in the first way or stating it in the second way. When I referred to and vice versa, that is equally applicable